fiber optic communication systems, and like I said, this is the basic objectives, and we'll look at this video.
Fiber was able to connect the world or to make people close to each other in a much more efficient way.
It's enabled us to be able to Twitter or email each other or carry a BlackBerry and be able to be within touch with anyone on Earth within seconds.
If you didn't have very high bandwidth, you could not do things like YouTube or any other type of propagation of video networks. You could never do pay-at-home kind of TV. Any of those things you could never do over copper. The bandwidth just is not high enough.
I have a 4-year-old daughter. She's going to tell me how much we need optical fiber within 10 years. Imagine an empty paper towel roll, and on the inside of that roll, it's like a mirror. And at the end of that, you have a little flashlight that you're using Morse code to get the light to come and be guided out of the end.
Optical fiber is a hair-thin strand of glass.
Extremely pure, that we use to transmit signals and data over very long distances.
The light carries data, and therefore it's a communication mechanism.
Telecom, internet, voice, video.
The way optical fiber works is it's two different compositions of glass. There's an inner core glass and an outer cladding glass. All the light is contained in the inner core glass. The fact that it has two different kinds of glass is what creates the ability for the light to always stay inside the inner core glass.
We use it in submarine, underwater applications, typically to connect like across the Atlantic.
You have multiple cables connecting Europe to North America to Asia.
Increasing bandwidth from continent to continent and just really making a difference again for the whole world. And that connectivity again just brings us very close together.
The second embodiment of work would be for other long-haul applications that go across land. We would call that a terrestrial application. Once you get yourself further into the network, you get into metropolitan areas around large cities where you have a lot of optical traffic, and then eventually we'll move into premises, somebody's house, a business building, multi-dwelling unit, and then there's applications within those buildings for optical fiber as well.
It has enabled video conferencing and communications. It's enabled the entire internet and all the services that go with it. In our homes, we would not be sitting in front of our PCs at home today participating with all these great services, video conferencing and so forth, without fiber optics. It's enabling receipt of many hundreds of television channels in your home, including high-definition channels. And ironically, it is the key enabler for wireless systems. All of those cell phone towers out there connect to optical fiber, and that's how the bandwidth gets to the consumer.
If you look at the history of optical fiber, the concept of waveguide propagation, it's a very old concept. Then in the 60s, there was a race to try to find a way to do that in a very efficient way.
Corning had done investigations years before, actually, in developing what they called fused silica, which is a very high purity glass. Not quite the purity that we needed, but Corning had a good foundation of understanding how to make glass in that novel way. But they built on that and did a lot of experimentation and a lot of development on getting that last bit of purity that they needed to make optical fiber a practical invention.
The key innovation was determining a way to create low-loss fiber by creating a structure that entrapped that photon and did not let it leave the fiber as it was fired down the length of the piece of glass.
Our scientists went to work on it. and in the late 1960s, early 70s, we had developed the first low-loss optical fiber that was practical for telecommunications.
The actual design is, fascinating, but it actually took many years before you can feasibly manufacture it in large volume. Corning not only invented the fiber itself, but has invented those manufacturing processes.
It's a very high-tech process, and only a few companies in the world are capable of making a high-quality optical fiber.
When people think about glass, they usually think about sand. So I'm going to get some sand and and put that in a furnace, and I'll get glass. Well, if you do that, you're going to get glass, but the glass is not be as pure or as clear as you need for optical fiber. You may make an optical fiber with that process, but the light will be able to propagate just a few meters, and then you don't have signal anymore.
Optical fiber is completely different. The glass is made in an entirely different way. It's a direct oxidation of chemicals to a glass in a flame, so it never touches any foreign material. So that is how the very high purity is maintained, which ultimately enables the production of optical fiber.
The first step of the process, called laydown, we take a ceramic bait rod. It's just used as a capture mechanism.
Silicon tetrachloride and other raw materials like that are delivered to the plant. We will vaporize that raw material and combust it, and that starts forming silicon dioxide.
The highest purity silica that can be produced. The result of that is a preform that's got loose particles of silica embedded on it.
As that process proceeds, then that cylinder of glass grows in diameter, and you're left with what we call a soot preform.
While we're building that layer up, we are also changing the glass composition in order to give us the index of refraction profile that we want in the final product. So the actual index profile of the final fiber is created in the very, very first step of the process. And it's very important that we never do anything to modify that profile in the subsequent steps of the process.
The next step in the process really is to consolidate or collapse or melt all those particles of silica together.
In consolidation, we do two major processes, drying and sintering.
We chemically dry it with chlorine to drive the moisture out of the preform.
And we also sinter it into a monolithic block of glass.
It's like we're baking the glass. It's not quite melting, but we're sintering the glass so that it densifies and becomes clear.
And that is called the blank, an optical fiber blank. From that point, it goes to the fiber draw, and that is where that blank is drawn into the very hair-thin fiber that we call optical fiber.
We hang the blank vertically, put it in a draw furnace, and unlike consolidation, we're actually melting at this point.
We set the blank down into the hottest part of the furnace and draw it down into individual strands. So we drop a large chunk of that glass, and the weight of that glass draws it down into individual strands of fiber.
And it is round to 99.99%, and it is the same diameter to within 1/10 of a micron over its entire length. So it's an extremely precise and extremely specialized process of manufacturing.
The most difficult part of manufacturing optical fiber is how complex the process is. You need to know everything from the glass properties when you start with that huge chunk of glass all the way down to what you're going to get optically in a small strand of fiber, and those properties change dramatically as you move through the process. So it's all about predicting what you're going to get from what you start with.
Glass has some very unique properties. It's stronger than steel as long as there's no defect. As soon as there's a defect, breaks just like that. So what we have to do is have an extremely clean environment, an extremely tight tolerance in manufacturing the preforms and then subsequently the glass. We monitor the glass as it's being drawn into fiber hundreds of times per second. to ensure that the dimensional tolerances of the glass are right.
Quality is it's probably the most critical piece. Optical fiber, once you install that, you are making open holes in the ground and you're putting a cable there, and you don't want to touch that cable for a long period of time. Same thing if you think about a submarine network. Imagine you have a cable now going under the Atlantic or Pacific Ocean connecting two continents, and you don't have to have a problem in the middle of that cable because it's going to be very expensive for you to go there and fix that. So that's why quality is critical.
The way Kearney understands quality is all the way from the raw materials to the use of the product, and making sure in every single step we meet or exceed our customers' expectation in terms of quality.
Quality is engraved in everyday operation of the optical fiber business, and that involves research and development, and production and customer support and sales.
We have embedded, again, quality architecture into our technology, our rigorous process, and trained our people to the quality principles.
We cannot allow any contaminant anywhere in our process because a particle of iron, a particle of nickel inside of this.
Yeah, these are just people talking, so we're going to go ahead, which is what we're going to go over. So just like copper, there's a lot of terminology or language that we use in the trade. So we'll go back and look at that, and we'll show you them actually making it later on. The three major functions of a fiber system, of course, is to guide the light from one end of the system to the other. And the lights are modulated to carry information. What do we mean by modulation?
Isn't it in regards to, I know it's all about that, like you're receiving a lot of information from several sources, isn't that right? Like
But modulation is a technique where we take the information that we're trying to send, and then we place it on another signal that we call a carrier. And the act of doing that is called modulation. What we're doing here, our carrier is light. So we're taking an electrical signal and putting it onto a light source. And what we're doing is we're sending millions of just basically pulses of light that represents the ones and zeros that we use in digital communication. Very seldom do we send analog information over fiber. Probably 99.9% of the information that's sent on the fiber is actually digital information. Now the function of the light signal is modulated to carry the information, but once we modulate it, we're going to have to demodulate it. So we're going to have to take it from light back to electricity somewhere. We refer to those as end electronics. So we have electronics that takes the light and converts it up, takes the electrical signal and modulates it into light. And then on the other end, we got to do what? We got to take the light and back into electrical signal so we can process it inside our computer. The cable is the term cable. So we know that cable is used two different ways. Cable is used to indicate a multiple conductors that are inside a common jacket. But we also use that term on conductors conductors that consist of several layers, right? You understand? So most of your fiber optic cables consist of multiple layers, and so this is a single fiber conductor, and it depends on. And of course, I didn't start my camera. And we'll see it consists of all types of different layers. So this is why this is called a cable, even though it does not consist of multiple conductors. Oh well. Where did it go? Where it comes from? So this is a typical cable. This is the conductor, and it's got two layers which we can't really see. We'll look at those in a minute. And then it's got different layers. And then, of course, this would be the actual, what we call the inside jacket. And then this is Kevlar. And then we have the outside jacket. So that's the multiple layers. And of course, the layers of all these cables are in there to protect, if you can see it, out on the very end. Not right here. You can see where it actually gets bigger, but it's protect that guy right there. That's the actual conductor of light. Now this is glass, and we got plastic. So basically, broadly, fiber is calculated is in two categories. We have plastic and we have glass. Plastic we use for short hauls, and the glass we're going to use for longer hauls. And it allows us to install the fiber and also handle it. So function of the major components, we have the connection mechanism. It's very important, since we're sending light, that everything in the system is aligned. So anytime I go through a splice or a termination, somehow we got to come up with a method where we can align these conductors, right? You understand? In protection, of course, if it's glass, we've got to make sure that we protect the end of that cable, even plastic, because what we're trying to do, of course, is so when we terminate this, or when we splice it, so you got two glass tubes, and if you splice it, we're going to have to make sure that when we get this right here, this cut right here is perpendicular. Right? Why? Because if the glass hits and I break it like that, then the glass is going, then that light's going to refract out of that thing, right? So aligning these two conductors perfectly when we splice them is very, very important. Making this a perpendicular cut, and also when we terminate them, you're going to have this little old receiver over here, and bringing this light tube into that receiver, and this is all the electronics back over here. And then, of course, this guy is glass. So what do we need to do? Well, somehow we need to protect that glass, because if we bend the glass too far, what's going to happen? Well, it's going to break. So we got to protect that glass. So this is what they're talking about, all these mechanisms that we'll look at. So this is a typical, this is called an ST connector. You can't see it, I'll pass it around, but the glass comes out with a little center right here. So all this is in there to protect and align this conductor when we put it into in protection. Got to protect the engine fiber from getting, of course, contamination. One of the losses that we have in the system is contaminated. So this right here is not a good idea. So what we have, even when we're using it, we would have an end cap. We would have an end cap that we put over this, and then we use alcohol wipes a lot to clean them off. We use what they call syringe grade alcohol. We don't use standard rubbing alcohol because it's only 70%. Syringe grade alcohol is at least 90%. So we use syringe grade alcohol because it has less impurities. So when we take them off, we clean them, and then when they're laying out like this, we keep an end cap over these things. But this is the protection mechanism. Also, we got to come with a mechanism where we can snap them together, and we'll look at that one. So this is one of the terminations that was done by the class. We'll let y'all look at it in a minute. Wait a minute, this is called a bayonet type. This is an ST connector. Color cups. Or we have splices too that we'll look at. We have different types of splices we'll look at. We have mechanical splices, which we'll work with, and then we have a fusion splicer. Mechanical splicing, the splices themselves are fairly expensive, but if you want to do one splice, that will go. A fusion splicer, the one we got, costs over $7,000. But if you were doing hundreds of splices, then this fusion splice gives you a lot better splice too, and it's a lot more mechanically sound, and we'll look at those too. So we'll play around with both the splices, and then of course how to terminate them. And of course, the end of electronics, this is the electronics that's going to take electrical pulses, signals, and convert them into light pulses. And then on the other end, we got to take the light pulses and convert it back into electrical signals so we can process it right. So this is a basic fiber system. These are shown in photodiodes, something we call a light emitting diode and a photodiode. Normally we use phototransistors, and then we have fiber cable between the two. Coupler combines two optical signals of different pulse paths into a single optical splitter. Complements a coupler. Wavelength division, multiplexing. What is multiplexing? Thank God for multiplexing.
Yeah, so you're taking Oh, okay. So you have different waves.
So multiplexing is a technique where we can send multiple signals over media. So media is what information moves through.
Yeah, so right now our media is glass.
Good.
And fiber.
Well, the media would be glass, right? Well, air's a media. Your cable TV uses copper. But if you think about it, how many channels come over that? How many copper wires? How many wires do you have come in the back of your TV? One. How many channels ride on that one wire? 1,000. Not thousands. Hundreds. We ain't got to 1,000 channels yet, thank God.
Yeah.
I mean, can you imagine?
9,000 channels. You got 9,000 channels.
So
9,999 exact.
So
Available.
Don't get the channel numbers confused with the number of channels. So multiplexing is a technique where we allow multiple signals to share the same media at different times. Well, it depends. We have two types. We have what we call baseband, and then we have broadband. Now your cable uses broadband. Baseband is what Ethernet uses, or Wi-Fi. Wi-Fi is baseband. What baseband means is we have multiple devices that share the media, but at different times. Okay, you understand? So what that means is that when when my computer is on this Wi-Fi, it has the total bandwidth that's allowed. But I'm only on it for a real short time. We send what we call packets. So the way Ethernet works, or not Ethernet, TCP/IP, which is the protocol that we use, divides it up into packets. And then we send out a packet, and then it releases the network. And then it checks to see if anybody's on there. If nobody's on there, it'll send packets. So what's nice about baseband, the less number of people that you have on the network, the faster it is. So this is why, in the morning, if you got wireless and you're checking your email, it's real slow, because there's a lot of people doing what? Checking their email. You get on there at 2 o'clock in the morning and it's going to scream, because odds are you're going to be pretty close to the last one. Broadband, what we do is we take the bandwidth of the media and we divide it up into multiple people, but that's where the modulation comes into play. So that's what your cable is, baseband. your wireless is, I'm sorry, your cable is broadband, because all those channels are on that same at the same time, and they're all shared. What is the bandwidth, by the way? We talked about that before. What's the bandwidth? The rate at what the media travels.
No,
It's the range of frequencies that a media can reliably pass. It's the range of frequencies that the media can. So on baseband, everybody's sharing the bandwidth. So if you got 100 megahertz bandwidth, you got 100 people on there, then everybody's getting 1 megahertz, right? And, if you think about, so I think Spectrum just raised their bandwidth up to 100 megahertz on their cable. It don't mean you get 100 megahertz. It's 100 megahertz on their cable. So a splitter, a multiplexer is what. So multiplexing. If I multiplex signals, then I've got to have a method of doing what? Demultiplexing. We have these devices we call multiplexer demultiplexers. Most people call them modems. Multiplexer demultiplexer. And that's why it got its name. So a modem has the ability to multiplex you onto a broadband system, and it's also got the ability to strip you off that broadband system, right? So everybody's got a cable modem on their house. Used to, we had phone modems. Y'all remember? Y'all go through that?
Oh, yeah.
We used to teach that too, how those things communicated with each other and how they talked to each other and set up protocols and all that other things. So these modems still have to do that. So we okay? So this would be a coupler. So that was a little wrong a while ago. That's why this would be a coupler. So a coupler allows us to multiplex. And then, of course, on the other end, we would do what? Yeah, demultiplexing. What we do here, how we multiplex here, is usually they use different colors. So we'll have like a red signal and a green signal, say. And then on the other side, we have a green filter and a red filter, and it will split them back up. And this would be a splitter. Redundant paths with a splitter, multiple receivers using splitters, demultiplexers. Are we okay? So what they do here is what they're talking about. So here you have different wavelengths. And we talked about wavelength in this class yet? Yes, we did, just a little bit. The first lecture that we had covered fiber just a little bit. These are, what I'm going to do here is we'll come back to this later. These are different ways that we connect this thing up. So let's just go ahead and get into the actual fiber itself. So fiber optic conductor consists of a what? A core that carries the light. It consists of cladding, which causes the light to reflect back into the core. It also protects the core. It also increases the size of the fiber conductor. We're going to see standard cladding that we're going to run into on most of your glass fiber is 125 microns. So what we have is we have this, and then inside would be the core. And the diameter of the cladding, no matter what the size of the core would be 125 microns. The size of the core is what's going to vary. But the size, if the cladding is constant, if the cladding is the same size, then we can use the same connectors. We can use a lot of things on the same, because that's what they make contact with, is they make contact with the cladding. And what happens is we have the cladding, and we talked about this before. We'll come up and look at that. Then we have what we call a coating. This is done on the fiber. So we have surrounding this. we'll have some plastic, and this is going to be the coating. And that coating, the coating is in there for protection. That's all it's in there for. And so what we have to do when we splice it is we have to get rid of the coating. And I don't know if we can see this or not, but I'll pass this around here in a minute. You cannot see the core and the cladding. Those are one unit. So we can see it with a fiber scope, and we'll let y'all see this. And this is not going to show up, but I'm going to pass this around. This on the very end, this is the conductor, this is the cladding, and this is the core. You can't split those up. And then right here where this little thickness starts, this is the coating. Okay. And of course, this is glass. So what you see on the very end out there, that's the conductor. And the conductor consists of the core and the cladding. And then what you look also, and you'll see the coating. Some people call it a buffer. Some people call it buffer coating. And this is there. That's in there to protect the clad and also increase the strength of the conductor. Are we okay?
There's not very many I use that one.
What's that?
I don't use that one a whole lot. That type. Where it's got the Kevlar involved.
Yeah, that's the actual cable that we would pull. Once we get to the actual unit, we'll get down to what they call the inside buffer, and then the coating. Well, I've seen some.
What I mean is there's a different cable we use altogether. I mean, in Castellium we have something similar to that, but there was one in the waste treatment plant where we had just a big, thick cable, with a black cable, and you have like 4.
Yeah, that's different. There's different types. This is an individual conductor right here.
Yeah.
And we call this is called a cable because it consists of multiple layers. Now we have different types of cables, premise cables. We have different types of buffers, and we'll look at some of those. And you can see a bunch of them over here on these diagrams. But I guarantee you it's got this right here. It's got the buffer coating. It's got the clad and the core. Right?
Yeah, no, they have that. It's just there's multiples in that.
Yeah, so this is a typical single conductor cable.
Would that be used for single mode, or would that still be used for multiple?
Same. All they do is they change the color of the jacket. So orange, if you see an orange jacket, it's multi-mode cable.
It's multi-mode?
And then yellow and blue are single mode, depending on the size of the core. Typical conductor is 900 microns, and that's all the way out to the outside jacket or the outside buffer. By the way, we have two types of buffers we'll look at. One of them is called tight buffer or tight jacket. And unfortunately, this is used, the term is used, and then we have what we call a loose buffer, or a loose jacket. This would be a tight buffer because the buffer or the jacket is in contact with the coating. So this is what I'm showing you here. This is tight buffer. So this is tight buffer. We have what we call loose tube. It's called loose buffer. It's called loose tube. And we'll look at the characteristics of why they use that. Usually if we're going to run it underground, we'll use what they call a loose buffer or a loose tube. If we're going, well, it gives it flexibility, plus it allows things to move around and it doesn't affect the actual conductor. Light flows, we already looked at this. Light, magnetic waves at extremely high frequency, these are lights. So light frequencies run from 1 times 10 to the 14th to slightly over 1 times 10 to the 15th hertz. But on those, 4.29 to 10 point, y'all don't have to memorize this, by the way, so don't worry about this. So visible light is anywhere between 4.29 times 10 to the 14th to 7.5 times 10 to the 14th hertz. And comparing that, this is our FM radio frequency. So our FM stations are up in megahertz. Your light's up in what we call terahertz.
That was gigahertz.
What's that? No, lights, the visible light, or the lights that we're going to be using is in terahertz. Yeah. That's fast. So this is the light spectrum, which we've already looked at. Now, what we do in light, once we get into these high frequencies, instead of using these times 10 to the 14th and all terahertz and all that kind of stuff, what we do in light is we give we don't give the frequency. What we do is we give the wavelength. So if these things are propagating through a media, then between that and this, we have a certain length of time, right? You understand? So light are usually, especially in fiber, we give the light is in what we call so 660 nanometers, this would be visible. 850 nanometers would be visible. And these are the wavelengths that we use in fiber optics, the predominant wavelengths that we use in fiber optics. I'm not going to say you're not going to run into more. Multimode depends. Multimode usually uses the 660 or the 850. Single modes usually use longer wavelengths. They use the 13s. And we'll talk about modes in a minute, if y'all.
I think it was 850 and 1550.
1550 would be single mode. I'm pretty sure. High frequencies are usually given in wavelengths instead of hertz. Every repetitive electromagnetic wave moving through a media has a length referred to as the wavelength. Wavelength is determined by the frequency of the wave relative to the speed of light. Light moves at around 3 times 10 to the 8th meters per second. Wavelength relative to light is given in nanometers, which is 1 billionth of a meter. This is the actual formula right here. So it's wavelength, which is the lowercase lambda. Lambda. That's what we use to represent light. C is the speed of light. So this would be the what? 3 times 10 to the 8th. And this would be the frequency of the light. And then what we do is we take this and we multiply it by 1 billion times 10. Right here inside these guys right here. For what?
For infrared, for
No, it's probably a wavelength. Probably it should be nanometers. Nano? You got me. My son's got some of those.
I want some.
Oh, I went too far. So all these are in terahertz. These are in, what do you call that? Petahertz. Exahertz. So, okay. So here, so what's the speed of the light? So speed of light, we're going to use what? 3 times 10 to the 8. So what would be the wavelength of 353 terahertz? So I would say what? Let's say my wavelength would be equal to 3 times 10 to the 8 divided by 353 times 10 to the what? 15th? No, 14th. 12, I'm sorry. We'll get that right in a minute. I should have known that. And this should give us the wavelength.
8.45 or 8.5?
Sounds like you're off a decimal point.
Times 10 to 17.
So 3 times 10 to the minus 8 shouldn't have to do that because this is considered to be a number. Oh, this is the minus 7th. Yeah, this is not in, then I multiply this times 10 to the, let me get this right, guys. I'll multiply it times,
I put 10 to 8.
what'd you come up with?
I got 8.49.
It's 850 is what it is. So we're off 2 decimal points.
That's engineering.
Huh?
That was engineering. Does that make a difference between engineering and science?
Well, what your engineer notation is going to do is it's going to stop right here, which is not in nanohertz. And what we need to do is stop right here to get it, I'm sorry, in nanometers, right? Understand?
So that's scientific notation?
Well, no, it's a form, we're going in engineering notation, but the way it's given is given in 3 digits, or I'm sorry, multiple digits. So what we do is we do this same thing every time, no matter what we come up with. It's standard to give it in nanometers. So to give it in nanometers, then what we'll do is we'll multiply it times what? What am I doing?
Billion?
We'll multiply it times a billion, right?
Time. 1.
10 to the 9.
0. Okay. To the 9. Equals. I still got it.
Now, this is not 1 times 10 to the 9th. Okay, understand? Yes or no?
The billion just keeps going up by.
Yeah, we need to take a break. Hold on, let's do this one and move my calculator up. Yeah, let's do this one first. 353,
Okay.
right,
Right.
times 10 to the 8th, right, terahertz,
Yeah.
divided by, oops, got that backwards, yes, sorry. 3 times 10 to the 8th, divided by 353 times 10 to the 12th equals that, and then I'd multiply that times 10 to the 9th, 850 nanometers. So it's not 1 times 10 to the 9th, it's 10 to the 9th, right? 10 to the 9th. So 3, now this is times 10, I'll use this one, times 10 to the 8th, right? You don't have to use parentheses because that's considered to be one number. Divided by 353 times 10 to the 12th. Okay, and then I'm going to hit equal, and that's my answer. And then I'm going to multiply this times 10, and mine is y to the x. I don't know what yours is. Mine's y to the x times 10 to the 9th, and that comes up and gives us, and I just blew it. I put too many in there. 10 to the 9th comes up to be 849.8, which would be 850 nanometers. Okay, guys, y'all take a break.
Now, if you do that a few times, you get it right.
We got another one in here.
We're always going to do 3 times 10, or 3 times 10 to the 8th. There's your 30,000, or 3.
And then your frequency is, in these are going to be terahertz, so that's 12. Now, in legal engineering notation, we move in threes.
Yeah.
But this one always goes in nanometers. So nanometers, we multiply that times 10 to the 9th every time, and we might come up and get 1310 nanometers, which would be illegal engineer notation, right? You understand? But wavelengths are these wavelengths are always given in nanometers. That makes sense?
Are you, am I going to be able to work this Friday?
Am I going to be able to what?
Am I going to be able to do this Friday?
I'll be out as far as I know. All I'll be doing is the files and doing that.
Well, I need that too. I need to, sign, I need to get, I was going to speak around this day, but yeah, but, you know, they always just have me first.
Yeah, I know.
So,
I didn't remember who said anything about it first, so I only was able to do 2. There were several people around. I think they got tired of waiting.
yeah. Today's 28.
All day long.
Yeah. Y'all hiring yet?
Oh, they've been hiring.
Huh?
They've been hiring. Crazy thing is they got like over half the shop. Really? Yeah. So they're.
I'm coming to your department.
My department's not hiring. They like to keep their employees low. We don't even have, I think, 10 guys in our department. We actually lost 2, and they replaced both of them with me, so they're expecting to get as much use out of me as they did the other guys.
Yeah, that's usually how it works.
Yeah,
They'll go until you can't go no more.
yeah.
You get that new car? Huh? You get that new car?
Now the insurance companies are being real picky about that crap. It's kind of getting annoying. So I'm waiting till one of my tickets drop off, which is next year around May. So then I'll be able to get a car then easily. Without it costing me like
'Cause I don't know what I did with the plastic fiber.
plastic fiber.
Yeah, we got a whole roll of it. Well, not a whole row. We got,
I didn't move it over there, did I?
no, I had it this morning.
Oh.
Well, plastic fiber's not as good as glass fiber.
Well, depends. How far you want to go.
Yes, the plastic's better for short distances.
Yeah, cheaper too. Electronics are cheaper, a lot simpler, easier to terminate. So there's a lot of advantage to plastic over glass, but for long distances, glass is the route to go. So let's do this one. What will be the wavelength of 231 terahertz?
We took 231.
So remember, speed of light is 3 times 10 to the 8.
We did that for.
So tera is times 10 to the 12, right? So it's 1 times 10 to the. So EE. So you'd use your EE or EXP key or EXE key on your calculator. Depends on what type of calculator you got. So this is a lower frequency, so we should expect it to have a wider wavelength, right? And I left that thing recording the whole time it was on break. So I do that all the time.
I don't know how to do it on my day.
Let me bring it up here. That was before Thanksgiving break. You know how that is. So 193 terahertz. Cable size, conductor size usually given relative to the diameter of the core and the diameter of the cladding in micrometers. So 50/125 would be a 50 micron core and a 125 cladding. 62.5 by 125 would be a 62.5 micron core and a 125 cladding. And this is what we're, by the way, the cable that we have, this is what we got. 62.5 by 125. 85 by 125 would be a 85 micron core and a 125 cladding. And then 100 by 140 would be, this is usually plastic, it's a 100 micron core with 140 micron cladding.
With that cable being so flexible, how do you not know that it hasn't been built? What?
We have meters we can put on it. We have light scopes. We got a, yeah, we can measure it, but also we got a light source. You just put it on one side and you point it. You don't put it in your eyes, but you point it at the ground. You can see the light go through it real easy. And then we have meters that would measure the loss. And we know the loss is supposed to be a certain amount per unit. But usually if it passes the glass, most people don't really, a lot of people don't, when they check it, they don't use the meter, they just put a light source on it.
Yeah.
And we got one, we'll show you on that, it's real neat. So this is what happens, we have two types of paths. We have, and we'll look at this in a minute, we have the core. And we got different paths that the light takes down the path. We'll look at that in a minute. What's neat is it just literally just reflects off that cladding, right? No, don't like that. And we already looked at one video. I think I have this on our server, by the way. So we call it the critical angle. And what we do is when we pass through So this guy, all he's got is just a light source that's concentrated. And he's got angles set up on both sides. And he has it every 5 degrees. So this is 0, 5, 10, 15, 20, 25, 30. So what he's doing now, he's coming at 0 degrees, and you notice that the light does what? Yeah, it travels straight through. But he started at 5 degrees, 10 degrees. Okay, now what you're probably seeing, that would be 15 degrees. But over here, so he's over there, he's on 20 degrees. But over here, he's just, can you already see it start what? It's starting to do what? Starting to refract or starting to bend. Ain't that neat? Yeah. And then, of course, when he gets, now notice here, it's starting to reflect. This is refract, this is reflect. And when he hits a certain angle, every bit of the light is what? Reflected. Now imagine we have this straight side over here. Well, now he's going, increasing, increasing, increasing. And as long as he stays below that critical angle, then we get total reflection. Once he gets above that critical angle, then we get what we call refraction. Does that make sense? So what happens is that's what they do. They have these two sides right here, which consists of the cladding. And these have different speeds of light travel through the cladding and the core at different rates. And so what happens if you have that at this interface between these two things where light travels at different speeds, we start getting refraction, right? You understand? And then if we can maintain this angle, then we get what we call total reflection, right? Everybody understand that?
Yeah, I thought the plan was to keep the light in the core.
Well, it is. So the light is traveling in the core. So here's the core, here's the cladding. Okay. So notice it's when it hits this interface between the cladding and the core, since they have different refractions, indexes of refraction or different speeds of light, it does what? It reflects. If you get above that angle relative to this, then it will start doing what? Then it will start moving through the cladding. We call that refraction. So as long as we can stay below that critical angle, then everything works okay. Total internal reflection, we okay there? Reduction of signal intensity. Of course, this is going to happen. We know for a fact, if I transmit light, we have different things that's going to cause, even wire. Every wire has resistance, right? So all glass has resistance to the flow of light. So the further you have to go, the light just automatically decreases in intensity over distance, right? You understand? And then we have what we call pulse spreading that we'll look at in a minute. So this is the same one that we talked about, right? So here we're below the critical angle. I've been saying that wrong. And what do we get? We get total reflection. If I'm above it, we get what? We get refraction. Everybody okay? I like some of those pictures like out in Colorado where they got them lakes out there and it looks like the mountains are go down and up, right? It's got two peaks because we're below or above the critical angle. And I think this is the same one we just looked at, so. You know, I'm probably looking at the wrong PowerPoint, so I went back and modified all these links and everything. For some reason, Corning, y'all know who Corning were? They are the people that invented fiber optics. And so they used to have a bunch of videos up there about this, but it looks like undoubtedly they've taken them all down.
They want to charge you for separate classes.
No, oh, for classes?
Yeah, they stress the idea of taking the classes.
What did you gather from them?
Huh?
Is that what you gathered from the interview or from the, where'd you get that? Take this class?
Oh, no, I saw some videos on them demonstrating some fiber, but they say that it's more ideal to go to the class. They realize they can make a lot of money. Yeah.
So they used to have a lot of stuff on Corning's website up there that now fortunately when you have the video, the links, they're not going to work on when they go through a PDF file, right? But I think what I'll try to do is I'll try to put yeah, this is the one I changed. No, this is the one I changed. No, that's not the one I changed. I don't know what I did with it. So, okay, everybody okay on critical angle? And that's the way reflection, everybody understand reflection? Reflection, of course, should be obvious. We understand that in mirrors. But refraction, what's refraction?
And also, where you're looking for where you're.
Isn't it where it's kind of coming outside of the fiber?
Refraction is what happens when, well, it's not, that would be true, because what happens is instead of going down the core, it refracts through the cladding.
Yeah. Is that a critical angle?
Is that a critical angle? This is one thing we got to be really cognitive of in fiber, is how far we bend that. We don't want to exceed that bend radius. So most of the time the bend radius on fiber is not where the glass will break, it's just where you'll cause it to get past that critical angle, and you'll get a lot of refraction instead of reflection, right? So one of the things we'll do when we have our meters hooked up is we'll bend the wire and we'll actually see the dB loss on the cable actually go up because we're exceeding what we call the critical angle. A refraction light travels through media at different speeds. Ranking vacuum is the fastest, air, clear glass, clear water, clear plastic. Light bends when it passes through materials that transfer light at different speeds. The bending of the light is called what? Refraction, right? And the index of refraction, and we're not going to work into this. So what they do when they yeah, this would be another calculation, but we're not going to do the calculation here because what they do is when they give your fiber, this is one thing they give you what we call the refraction index. To calculate the refraction index is they use the speed of light in the vacuum compared to the speed of light in the medium. Right? You understand? So if they have the same numerical index, then we won't get reflection, because that'll be glass on glass. But we got to, yeah. So we got to have different coefficients. We got to have different refraction indexes. The critical angle, if light moving through one material strikes another material with a lower reflection index below a certain angle, we call it a critical angle. Virtually all the light will be reflected back into the original material. At or above the critical angle, most of the light will refract or pass into the other material. It might be at an angle, but y'all understand this? Are we okay? So these are some refraction indexes between the core. Now these are different. So we know what this means. 5125. What does that mean? Well, the core would be a 50 micron core with 125 micron cladding. 62.5, 125. That's what we're using. I don't know if it's Corning or not. We'd have to look at it. AT&T makes fiber. Plasma makes fiber, and Spectrum. These are the three companies. That's not the cable company. I don't think it might be. So these are different companies that make different. And this would be this would be the wavelengths. They didn't give any wavelengths down here. But I'm sorry. So Corning makes all the way up to 1300 nanometers. And AT&T makes up to 1300 nanometers. What did you say? Yours is 13? You say yours is 13?
Wavelength?
Uh-huh.
Yeah, we test 850 to 100 or, yeah.
1300. Numerical aperture. The critical angle is usually specified in, this is what they threw out, a bunch of this stuff, you know. So the critical angle is usually specified as a trigonometric sign. So what we're doing is we create, in fact, if anybody had, well, even geometry, the way you'd break a triangle down. So what we would do to solve for a triangle that looks like this, so this forms a triangle, right? Is what we would do is we could come up here and we divide it into half, right? You understand? And this forms two right triangles. By this angle. And since the sums are equal to 180 degrees, no matter what. most of us know that this long side of a right triangle is the hypotenuse. So that's the hypotenuse. This is the opposite side, and this right here is the adjacent side to this angle right here. And this is called. So what we're angle, no matter how I spread that out, if this right here was 11.5 degrees, these guys would have exactly the same ratio. They would have the same ratio for that angle to maintain a right angle, right? You understand that? So numerical aperture of 0.2. Now, if we wanted to get the angle, we would take the sine minus 1 if we wanted the angle. So when we buy these cables, so this is some cables put out by Corning, and these are the apertures, another level of numerical aperture. Most common, right? You understand? You notice all these. So I can get that angle if I wanted it. So if I wanted what 0.2 was, which is what we did, that's about 11.5 degrees, right?
11.2. Yeah. 11.5.
But if I wanted to know what this one was, 0.29, then I could say 0.29, and then I'm going to hit invert. No, I'm sorry, wrong thing. I hit the wrong thing. 0.29, and then on mine I have to invert, and I would put the sine minus 1, and that would be about a 16.9 degree angle. So the bigger the numerical aperture, the bigger the numerical aperture, the more the bigger angle it can handle, right? Does that make sense? You still get internal reflection. If I go past this angle, then we're going to start getting what? Refraction.
Refraction's bad.
Refraction's bad. So if you get it past it, you're not going to get any light through the cable if you bend it too much. Or if your light source doesn't hit at an angle. So that's why when we cut these things, we want to make them perpendicular, because if you come off and when you cut these things, if you come up and get any slant at all, and this light's going to come over and hit this, what's it going to do? It's going to refract, and the refraction could cause it to go past the critical angle. If it's already coming in, if it's already coming down the cable like this, and then it hits that, and then it refracts even more, then what that's going to do is you could get past the critical angle. So when we cut these things, somehow we're going to have to come up with a method where we can get a perpendicular cut. And we'll show you how to do that. We have devices called cleaves, which we get perpendicular with. And then we sand them perpendicular too. So there's a lot of techniques to terminating these things, and also for splicing them. Attenuation, we know what attenuation is. Attenuation is usually measured in dB. We've already talked about dB, right? Two causes of attenuation, of course, is the cable itself. The fiber attenuation itself. So all fiber has attenuation. It's just like all conductors have resistance. Right? You understand that? So that means we're going to lose light over distance, if the cable is perfect. Right? You understand? But then what we have control over is connection loss. When we splice these cables together, sooner or later we're going to have to splice them. Right? You understand that? We've had the cable get broke a couple times here. So instead of running new cable, what did they do? They just spliced it. So, and then of course, sooner or later, the cable is going to have to come to an end. So we're going to have to learn how to terminate these things too, right? You understand? Attenuation, on fiber optics, we give dB per kilometer. And we'll look at this other thing to start off with. Everybody okay so far? So this is caused by the cable. We can't do anything about this. So as the distance goes up, then the loss goes up. Everybody understand that? Then we have we cannot make glass perfectly pure. So what happens, we got these little imperfections inside the glass, even though they explained it, it's very minimum, the technique they'll go. We'll show you how they do that. It's so neat how they make fiber. And notice they don't use sand, they use silica, right? And they use different methods of doing this, and it's really neat. They'll start off with a glass tube, and then they'll vaporize the silica and push it down that, and they do it so precisely that it forms a layer on there, kind of like the layer that looks like on fluorescent bulbs. And then they'll heat it up, and all those different layers do what? They just combine together and then they pull it. It's the neatest thing. But if you got any impurities, when the light hits it, it's going to cause it to do what we call scattering, which will cause loss in the cable. Of course, we have no control over this. Y'all understand? All they give us is the guaranteed loss per kilometer. And that would be including everything that they've got. Okay. So these are typical attenuates. So single mode with a 9 micron core with a wavelength of 1550 would only have 0.25 dB per kilometer. Wow. Still pretty good. Then we get into what we're using. So ours is going to be 62.5. And we're going to run this at a wavelength of 850. So ours is multi-mode down here. And ours could have up to what? 4 dB per, but it's still for a kilometer, right? You understand that? So the loss will be less, but you can see single mode. So what we'll do, multi-mode is what we use multi-mode for, is we use that inside buildings or short runs. Long runs, we're going to use single mode. So AT&T, what do they use? Single mode. They use single mode fiber.
Well, that's for housing, but for terrestrial, going across land.
What do you mean?
The grade gets a little.
The best we got is multi-mode. I mean, that's it. I mean, I'm sorry. The best we got is single mode. Yeah, single mode is the best we got. So this is the main thing that AT&T uses is they use single mode cable. Now, when we get inside our building, we use multi-mode cable because of the cost differential. Well, believe it or not, single mode is that the multi-mode cable that we use. We'll talk about this. The cable itself is more expensive on single mode cable, but it's the electronics that's required. Single mode requires extremely complex electronics. Multi-mode cable, we can use LEDs. When we get into single mode, we're going to have to go to laser because of the way it operates. So the end electronics and everything in single mode is a lot more expensive than multi-mode. So we have multi-mode. We'll look at that in a minute. First of all, we need to know what a mode is. Causes of attenuation. The one that we're responsible for is splices and termination. The rest of them is the responsibility of the company that makes it. One thing is trying to get that core to come down the exact center of the glass. So we call this core offset, and that's one thing that they give you. It's very, very precise how close they get that to the center, but it cannot be perfectly in the center, right? And then if I bang two cables together, even though their cladding is aligned perfectly, if they have different core offsets, then if these cores don't match up exactly, then we're going to get lost in our splicing. But it's not our problem; it's actually the problem with the cable, right? Core the cladding, the ovalarity, or how round is it? Did you hear what he said? It was within. I forgot what it was. How perfect, 99.999% round is what the guy at Corning said is the glass that they make. And so it's pretty round stuff. But we're talking about Corning compared to some of the other companies that might not follow the strict guidelines that Corning does. So this is non-singularity. So they're talking about the core offset is less than 1 micron for this single node at 1310 nanometer to 1510 is less than 1 micron. Multi-node, I guarantee it's going to be less than 3 microns. Plus or minus 2%. Well, plus or minus 2% of 1 micron is not even enough to think about, right? I need to go get one of our light sources. Y'all go ahead and take a break.
Here, what we have is an optical.
The audio's not playing.
See what they do, he's talking about.
Oh.
Here, what we have is an optical link with optical fiber transmitting this video, and actually we're showing the attenuation of the thing. Now, here I have a traditional optical fiber, and what happens is that when you bend the cable with optical fiber inside, you start losing your signal by increasing the attenuation on the link. So we have been developing new technologies that improves both the optical as well as the mechanical properties of the optical fiber. And now you can do things like that. You can bend the fiber, you can pinch the cable, and you see the signal is still going there, and there is almost no attenuation. You can do even more. So this cable is much more robust for deployments. And how you can use that? You can actually staple those cables on wall like that, without having much loss or attenuation in the signal. That enables much faster deployment and much lower cost to bring high-speed connectivity to your house. Link with optical fiber transmitting this video, and
But so what happens is we'll come over here on this side of the cable and we'll create a nice pulse of light. and then we send that through the cable. Well, what happens when it gets out on this side, it's going to end up like that. Okay. So the one getting there first, these would be the actual rays, and the one getting there right would be the critical rays. You understand that? So what happens if we don't try to do something, and this is what affects the speed of how far we can go in different types of cables. So if I send in a series of pulses like this, then what could literally happen is they could do what? So the actual rays of this one is going to overlap the critical rays of that one. So what my receiver actually sees is it sees this stuff right here. And now it's not getting these nice clean pulses, it's getting all this garbage, right? You understand? So that's what we need to understand is this is what limits the length, this is what limits a lot of things on these different types of cables, is that we can't send light pulses down without running in these critical rays and these actual rays. And that's what's nice about single mode cable, we'll talk about that in a minute, is the actual rays and the critical rays are basically equal to each other. Multi-mode cable, we do have actual rays and critical rays, but it's going to make the electronics a lot cheaper and sometimes the cable a lot cheaper. And this is what they're talking about, received signal overlapping. Y'all understand that could cause the receiver to receive the wrong information. Modular dispersion, that's what we just looked at. Mode. So here's a mode. What is a mode? What is a mode? The light can travel through the cable. So single mode only allows one path. Multi-mode allows multiple paths. So a mode is a path we can find. Chromatic dispersion, this is light of different colors traveling different speeds. So this is, what is laser, by the way? Well, I know what does laser stand for? Anybody know what that is? Y'all know that's an acronym, right? Close. Light amplification by stimulated emission of radiation. But what it is, it's light moving at one color. It's one color. It's one color light. So the problem, so one color light means we don't have chromatic distortion, right? Or dispersion, right? You understand that? Because not only do we have critical rays and actual rays, we have lights at different colors moving at different speeds through the cable. So I had one real good video where the guy says, I've got two cars, one of them's red and one of them's green, you know, and they start at the same time, but one of them's going 65 miles an hour, the other one's going 55 miles an hour. Well, what happens over distance is the one in 55 keeps doing what? Keeps dropping back, right? You understand that? So that's the same thing true with light, because light, different color light wavelengths travel at different speeds. So if I don't have an extremely pure light transmitting, then we're going to get chromatic dispersion. If it's got any other frequency in there, it's going to create chromatic dispersion, which means the light's moving at the faster frequency will hit the receiver before the light's moving at the lower frequency.
Wasn't that the whole point? Each color will move at different frequencies. Each color moves differently.
Well, they move at different frequencies. Well, what we're saying is if I don't have an extremely pure light, then we're going to get, not only are we going to get modular dispersion, we're also going to get chromatic dispersion. And chromatic dispersion is going to do the same thing that modular dispersion does, right? You understand? Which means it's going to spread the pulse out as it moves through it.
You say module.
Modal. Thank you. And then material dispersion, this is the actual material or the glass that it's made out of, right? You understand that? Are we okay? So we have all these different things that's causing the light to travel at different speeds. So what do? Well, we'll move from regular light over to laser. As soon as I do that, you're talking about very, very complicated devices. A laser LED costs hundreds of dollars. A regular red LED costs 15 cents. So you're talking about the end of the electronics that's required to do light at one color is going to be more expensive. A multimode fiber that allows light to travel different paths through the conductor. Typical core sizes 50, 62.5, and 100 nanometers. We're using 62.5 is the core size that we're using. Stepped index, a multimode optical conductor that does not control the light path. Graded index, multimode optical fiber that controls the light path. Single mode, we don't have to worry about. Multimode, though, means we're allowing multiple light paths. If you allow multiple light paths, it means the lights are going to arrive, it's going to spread. We're going to have a lot of modal dispersion, right? You understand? If they're different colors, it's even going to be worse. Everybody understand that so far? Okay. So stepped index, this is stepped index. Plastic is stepped index. So here I'm doing different colors. Different colors move at different wavelengths. So they would be bouncing off the sides all over the place. So stepped index means we don't control the path. So it's bouncing all down that cable, right? You understand that? Everybody okay? This will be the cheapest cable that you make, stepped index. So this is stepped index right here. This is plastic. So we get a lot of dispersion out of this, right? Whether it's modal dispersion or if it's chromatic dispersion, we get a lot of that. But this stuff is not made to run each long length. And it's very rugged, very cheap. So a lot of industry that's not running over long lengths, you're going to see them use a lot of this. The end electronics is real cheap. We use LEDs, very cheap for this system. The problem is that it does a real good job. Normally we use this, not for its speed. We use this stuff for its immunity to interference, electromagnetic interference. Fiber is totally immune to electromagnetic interference. So I could have cable running through the air. If I've got copper and lightning strikes it, we've got big problems. I got copper, I got this running through the air, lightning could strike it directly and makes no difference. So this guy here is immune to electromagnetic interference. So a lot of times we use fiber for that reason. So connecting from here to building A up there, we wouldn't necessarily have to use fiber, but it's running underground and it's running outside. So what do we use? We use fiber. So all the buildings here are connected with fiber. Once we get inside the building, everything's connected with glass, with either copper or connected to Wi-Fi. So this is stepped indexed. So it's like, now when we get to graded index is the most expensive fiber we have out there. So this cable is built in layers. And each layer has a different coefficient of refraction. So what happens is the light literally bends. It don't bounce, it literally bends. So it starts off like this and it bends and then it comes down and it bends and goes back and forth. So this is what graded index looks like. So here we still have a dispersion over the cable, but it's going to be a lot less than step index because that step index is affected by everything, right? You understand? Step index is the cheapest. Graded index is the most expensive as far as the fiber, but the end electronics is the same. So graded index, we get further distances on greater index with less attenuation. Well, attenuation is the name of the game anyway. So we have less attenuation, so we can run graded index further, but the electronics is exactly the same for step index, and graded index uses the same electronics. So if I've got a system that runs on stepped electronics, I could just hook up a graded index multimode cable, and it would know no difference. But this is the most expensive cable we got out there. The only thing we get from graded index is we can run the cables further. Which means higher speeds, right? You understand that? So this is a pretty good picture of graded index. So we're running graded index. So our cable is multi-mode graded index cable, which is the orange. And this is just showing you the profile.
Multi-mode graded index.
We have multi-mode step index and we have multi-mode graded index. Okay. And if we went back and looked, you could tell the difference. Normally they don't differentiate between it, or do they? Yeah, but what we do is we look at the attenuation. So here's 960, so this attenuation right here is 125 to 250. This is going to be stepped index. These right here are graded index, right? You understand? So look at the difference between the dB loss. So stepped index, odds are we're going to use that for real short hauls, and it's probably going to be plastic. We could get stepped index glass. Which one of these would be that? I don't know. But, so y'all okay on that? So single mode only allows light to travel one path. That's why it's called single mode. Requires an extremely lost core between 8 and 10 microns. And what's the light source going to be? It's going to be laser. So right off the bat, even though single mode cable is cheaper than graded index, where graded index has its advantage is the cost of the electronics. So a graded index system would cost less than a single mode system. But if I'm going to go extremely long distances, then we're going to have to use single mode. So AT&T uses single mode.
Can you interchange in the midstream?
Only if you, well, probably not, because they run different wavelengths. So your cable is not only matched to a certain, it's also matched to a certain wavelength of light that it will carry, right? You understand, which would be your carrier. So here's the basic wavelengths right here. So single mode uses a longer wavelength. So that means fiber that's been optimized for 850 will have a problem with 1550 or vice versa. That makes sense? Mm-hmm. And then it would be hard to match them because the core diameters are totally different.
Start with one, you got M. You got M. Start with those, you got M.
Yeah, and then if we wanted to go, we would probably go through electronics. So like when we come in here, so we run fiber over to the Birmingham campus, I think. I don't know. Used to we had a T1, which was it might still be a T1. That might be why we have so much problem. I need to check on that, talk to Jim and see how we get. And T1 is a telephone system. It's a twisted pair telephone cable that's rated at, I think it's 65 kilobits per second, so it's fairly slow. And I don't think we've switched over to fiber yet to go over there. But eventually we're going to have to go from fiber back to electrical, right? You understand? So eventually we're going to have to receive this. So we receive fiber over here, and then we run it through our switches, and then they convert it to electrical. And then the access points, the wireless access point hooks into a switch. We have hubs. Originally when we put, what is a topology? Anybody know what a topology is? If you're in the network, you'd understand topologies. Topologies are the way things are connected together. And we have three basic topologies. We have what we call a bus topology, which would be this. So that Profibus over there would be a bus topology. So you have one main conductor, and then you terminate this guy, right? You understand? And that's what that last switch is over there. So that Profibus over there would be a bus topology. Then we have a star topology, which would be this. And so this guy in the center was originally called a hub. And what it was is when this guy transmitted, everybody received. On the entire network, everybody received. Well, what that did is that slowed it down. So they went to something they call a switch. So now we don't use hubs anymore. We use switches. A hub. Well, what a switch does is when I send out an address, the switch is a computer. So one thing the switch automatically does when I hook a computer to a switch, it identifies that computer by what we call a MAC address, which is a medium access control access. Now the switch knows every computer that's on it. So if I come up here and say I want to go to this computer, what it does is it establishes a path to that computer, but it doesn't affect any of the other computers on the network. Now, if I tried to get to that computer, then it would slow me down. But as long as I'm communicating with somebody else, then I get. Then we have what we call a router. What's a router? A router is what we use to establish what we call subnets or individual networks. So what I would do is I would be able to have multiple networks, and then out here I would have a switch that divides the network up. So a router we set up a network in what we call subnetworks, subnets. So if you've got a wireless, you got an access point, a wireless access point, most of them you buy now has a built-in router, so you can hook up like 3 or 4 different routes. And then on that, you could hook up switches to hook up a bunch of computers. So a router divides a network up, and then a switch takes a network and allows us to, it's not actually divided up, but multiple communications. So when we go between these different medias, we could have different things. So my router, we could come in with fiber on if it's got a fiber port. We could come up with fiber, and over here we could have electrical, right? So this is single mode, and this is multi mode. So the core on single mode is so small that the light travels down one mode, which is pretty neat. It does bounce off the side a little bit, but it's very, very little. And then what we do to get rid of chromatic dispersion is we use laser. So that means single mode is going to have the lowest attenuation, and it's going to have the ability to run at the higher speeds. And believe it or not, it's cheaper. Single mode conductors are cheaper than graded index multi-mode, but where it gets you is on the electronics. Step index, cheapest cable, cheapest electronics, slowest speed. Graded index, most expensive cable, cheap electronics, faster speed than stepped index. And then we have single mode. The cable is cheaper than multi-mode cable. That's not graded index multi-mode cable, but it's got the most expensive electronics, but it's the fastest speed. So which one you use is what you want to do. You want to use get the cheapest system that you can put in there and run at the speeds that you need to run. Does that make sense? Yeah. So yeah, you could install single mode cable, but you're going from here to down that room right there, and you're running single mode cable when you might have been able to do it with plastic, right? You understand, and not degrade the speed that you were running at. Save yourself a ton of money. It's just like I could go in my house and I could run all 12 gauge wire in my house. It would handle 15 amps just perfect, but it would also handle, 80 amps too. But so this is just an example of core sizes. These are actually, this is a times 200 scope. So what we can do is we actually can see the core. So what you're going to do is you're going to see this little black dot. And this little black dot you're going to look at is the core. And everything that's surrounding is the cladding. So it's got a little button on here. You turn the light on this, and it's focusing. So that little block in the center is the core.
Okay.
But notice, what you should notice is it's pretty standard So standard cladding that we use is 125 microns.
And that doesn't vary.
Well, it does vary, but the primary cladding size is 125 microns. So you can look at all the cables, that all the different conductors that they gave out. Now, of course, in plastic it would be a little more, but yeah. So look, so Corning, 50, 125, 65, 125, 85, 125, and then they get to this guy right here, 100 over 140. So look, the primary size is what? 125. That would be your cladding. This guy here's got a big core and a big cladding. Exactly what this is, I'll let you know.
Underwater. Long distance underwater.
Could be. But usually when it gets to us, it's going to be 125, a 125 cladding. So it means a lot of your conductors, a lot of your connectors are the same, right? You understand? Because what this guy sees, it don't see the core, it sees the wire, it sees the cladding. Yeah, I want y'all to try to see that little hole in the center. That's the conductor.
How many of those light over here? You get a glimpse of it every now and then. But you really can't.
Yeah, you can. You can see the little old tiny dot.
Yeah, you can get a glimpse. Like it's hard to focus on it for any length of time. You catch it.
This is multi-mode cable, but the cladding is the same, and you're not seeing. You can't see the core. Everybody understand that. You cannot see the core. The cladding and the core are inseparable. They are one unit. They are fused together. They are made together.
And that's what you talk about when you go down to two.
Yeah, well, let me.
It's actually bonded together when they. What did you say was the word?
Yeah, it fuses. It's fused together. So cable fasten insulation, graphics, videos, fiber. I don't see one that says those ones that I've downloaded. These are, what are you looking for?
Oh, I just want to
Oh, thank you. I'm sorry. I thought you was looking at something. It's one of those ads you can't get out of.
Yeah, I just turn my head.
Every time you talk on the phone or go on the internet, when you say or type travels to its destination through fiber optics. Voice and data gets transmitted via pulses of light through air-thin glass fibers. Those fibers start out as large glass tubes. First, workers unwrap the tubes. Then they submerge them in a corrosive bath of hydrochloric acid that removes any oil residues. Then they send a tube into each end of the layer. As the tubes spin, they're heated with a hydrogen-oxygen flame. When the glass turns white, it's getting close to hitting peak temperature. At about 3,500 degrees, the two tubes fuse together. They put this new longer tube onto another lathe. As the tube spins, they inject a mixture of chemical gases inside, while a traversing burner heats everything up. The gas mixture contains liquid forms of silicon, an abundant chemical element found in nature, and germanium, a chemical element similar to tin that's used as a semiconductor in transistors and other electronic devices. As the gases heat, they undergo a chemical reaction that leaves a white soot on the inside of the glass tube. The heat fuses the soot, forming what will eventually become the core of the optical fiber. The glass tube itself will form the fiber's covering. When there's enough fused soot, they turn up the heat until the soot itself turns into glass. Then they heat the glass tube enough to soften it, and to soften the new glass inside. The intense heat eventually makes the tube collapse on itself to form a solid rod. The internal structure of the optical fiber has been achieved, but it's in the form of a big bulky rod called a freeform. So the next step is to thin it out. First, they excise the freeform from the uncollapsed section of the glass tube. Then they install it vertically into the drawing tower, which will draw out the final shape. The drawing tower's oven heats one end of the freeform to 3,600 degrees. The glass softens. Gravity helps pull it down, like honey drinking from a spoon. Then, using a block of glass as a weight, they stretch the soft glass and keep stretching it until they form the thin glass fiber. A series of pullers measure the tension on the fiber as it's being drawn. A special monitor makes sure the fiber is precisely the right diameter, just 5/1000ths of an inch. Then the fiber passes through UV lamps that bake on an enclosed coating to protect against dust and other contaminants. Finally, the fiber is rolled onto a drum. From here, it's either shipped out as is or put into a cable. Fiber optic cables are expensive to produce, but they're smaller and lighter than traditional copper cables. They carry more information and need fewer repeaters to keep the signal from deteriorating. And unlike copper cables, they're immune to electromagnetic interference. They're also hard to tap without being detected. And all this is made possible by a complicated process based on a very simple principle: light traveling through glass.
What do you think?
Good.
Is worked by internal combustion, a process that happens in each of the engines.
Internal combustion. CSCI's Bay is pretty interesting, right? You see that they put that different silica compounds in there. They heat them up, they fuse together, and then they just pull. It always amazes me how precisely they can make that thing just by dripping it out like that at the bottom. Of course, once they get it down there, they have all these sensors that pull it out and they make it flow at an exact right. Yeah, it's the gravity itself. Yeah. to get it started, then they start running it through the wheels that actually set the right tension and everything on there. Well, yeah, but you say glass breaks, but the way I compare it to is aluminum and aluminum foil. If you get something thin enough, it becomes extremely flexible. So this is glass, guys. This is glass, but it's so thin, it's flexible, and you can pick up a drinking glass and you can squeeze it with your hand and you can feel it give. But aluminum, if you get a sheet of aluminum that's big, you're not going to do anything. But if you get the aluminum thin enough, think about aluminum foil. That's a metal. Yeah, you could write definitely. So it's just extremely small, so it becomes very, very flexible, right? You understand? Like you get a chunk of copper, you can't bend it, but if you get it thin enough, you can do what? You can start bending it. And that's why that's what they do with stranded. They make the little individual strands are so small. Now they become what? They become flexible. So yeah, we think of glass as being this glass back here on this thing right here, and we don't think of it being this small and this thin. It becomes very flexible. Huh?
It makes sense. I know it's all.
Yeah, this is glass. This is glass. This is glass right here. You see, it's wrapped around here. I can come up here. I can twist it. Now, of course, if I was to come up here and take it in a pair of pliers and push it together like that, it would break. Right? You understand?
It's got a breaking point.
Yeah, it's got a breaking point. Just like aluminum foil, it's got its breaking point. I think over time, aluminum foil has actually got thinner.
Yeah.
By the way, this is called a pigtail. So a lot of stuff that AT&T makes is termination is not easy. Y'all gonna be able to terminate, and we're gonna do it manually. Well, it's all done manually, believe it or not. It's just that we have people that have the equipment that can really do these terminations. And so what AT&T usually buys is they usually buy these things they call pigtails. And then what they'll do is they'll splice it. Could do that. They'll splice this on either using a mechanical splice or using a fusion splicer. Now, of course, AT&T basically fuses, splices everything. And but this would still be inside right here. Normally, the conductor they run ribbon cables a lot. So ours is not a ribbon cable splicer. Ours is a single strand fusion splicer. And you're going to look at it and you're going to say, that thing costs $7,000. And I'm going to say yes, but it's a little tiny thing. It's in the other room. Mode field diameter within most of the light travels, and it's got a wavelength, but I guarantee you it's not going to work, because I think every one of these came through Corning. So they used to have a really good yeah, see, every one of these are through Corning, and it looks like they've taken all their free videos down. But I could probably find similar ones on YouTube. It's just that I didn't realize it until I was going over it. Bandwidth distance. So bandwidth is what we use for copper. What we call the fiber, they call it the bandwidth distance product. Megahertz per kilometer. Okay? Except for single mode, it's called picoseconds per nanometer per kilometer. So here's some typical bandwidth distance products. So multimode stepped index, which we looked at, would be 5 megahertz per kilometer. Stepped index glass would be 20 megahertz per kilometer. Multimode graded index is around 600 megahertz per kilometer. Multimode graded index running at 1300 nanometers is 1000 to 250 megahertz, 2500 megahertz. Then we get into single mode glass running at 1310.
Wow. 76,800
per kilometer.
per kilometer.
So if you went 2 kilometers, you would half it. If you went 3 kilometers, you would divide it by 3. So that's why they do it per kilometer. So it's very easy to calculate in this distance right here. So now you know your speed per. If you go 10 kilometers, you would take that and divide it by what? 10. So stepped index plastic, which runs at 660 nanometers, it's 5 megahertz for a kilometer. If I was going to run it, and that's only 5 megahertz, right? You understand, per kilometer. If I ran it 2 kilometers, it'd be 2.5 megahertz, right? Yeah. So yeah, you divide it, but just by the number of kilometers that you're going to run the fiber. So you can see why AT&T uses this guy right here. Because they've got fiber running miles now. You don't see much of it anymore, but you used to see these guys planting this orange cable all over the place. I mean, really neat, those machines they had that would. Yeah, but they could calculate the distance, so they'd send it down and actually bring it back up to where their junction boxes was. And it was those things were so neat. But I can't tell you the last time I've seen those.
I have what is it? Called sheeting.
I don't know what they call it. All glass fiber, glass core and cladding, single mode, used by telephone, CB, cable, television, network, backbones, multimode. So multimode is usually used inside premise, right? You understand that. We usually use multimode cable inside premise. Real short runs, we might use plastic. So like I said, all the fiber on both our lines over there are plastic. And we need to replace one of them, by the way. Fortunately, we don't use it. Plastic, though, so this is plastic. Let me strip off some of that.
Now the cladding and plastic are together on the.
Yeah, the cladding and the core are fused together, and you cannot separate those.
I don't know if that's true on the plastic.
Yeah, so it's fused. Now this one's been nicked. We got one on our lines that's been nicked, so we really need to replace it. I'm looking for the other end. There it is. So this is the light source, so it's I don't know if it's laser or not. Don't shine this in your eyes. And so this is the light source. And that's what, to me, that's so neat.
That is.
Look, it's passing through all this stuff. That's okay, it sticks in there really. So this is a neat little tool. It doesn't measure the dB loss, but you really don't have to. All this does is we know that it passes light, right? It's hard to believe that light is doing what? Traveling around that thing.
Is this laser? Yeah. Yeah.
It don't develop a laser beam, because a laser beam would be well defined. It's actually spread out. I don't know if it just because it's red don't mean it's laser.
It's used in the medical field a lot. Check the gains out.
That is neat. Very neat.
And this is just a fiber light source. That's all it is. This is really, really cheap. So it would be real good to tell right off the bat if you got broke wires, broke conductors or stuff like that. And then we got the dB meters that we'll look at where we actually measure the loss. So we'll do that. One of the labs that we'll do is we'll take a fiber cable and we'll measure the loss over cable over distance. And this is not really important to understand. This was just what was covered in that other textbook. The different methods they use: hard clad silica, plastic clad silica, advantages, disadvantages, plastic optical fiber, PLF, multi-mode stepped index. And of course, we know the advantage of this is what? It's very what? Cheap compared to the other fiber. It's very rugged. Then we get into buffering. Tight buffer. People call this a buffer tube. They call it a tube. So what we have is we have the fiber itself. The fiber consists of what? Consists of the core, the cladding, and then a buffer coating. You all understand that? So we got three things that the actual conductor consists of. And this is on glass fiber, by the way. So that would be the conductor. Then what we do is we normally take that and then we put it inside a jacket. That they're going to call it jacket. People call it a buffer. A buffer is a go-between, right? You understand that? That's something that's a go-between. So basically on glass, we have the conductor itself. The conductor itself consists of, so this conductor right here, it consists of the core, which we can't see. Then it consists of the cladding. Then it's going to have a buffer right here. And this is called a buffer coating. And then we have the jacket, right? You understand that. And the jacket has one function, even in electronic, is to protect it against the environment. It allows us to pull it, it allows us to do something, and it protects the table. A tight buffer, and I don't think I've got some loose tube over here. I need to go back over there and go through the box over there. We usually teach this class over in A building. And then we've got a lot of our fiber and stuff over there, and I know I've got some loose buffer. But tight buffer, the actual buffer is in contact with the buffer coating. Everybody understand that? We use this inside a lot. I don't think this is that. This is a, yeah, but you have different techniques. This guy here does not. This would be. This right here would be considered what we call a loose tube, but it's got Kevlar in the center. If y'all come up here, we'll look at this. This is not going to work out on the camera. So what we're looking at is we're looking at the coating, the buffer coating. And then what we do, you got to be real careful because you just double clip real easy. What's your eyes? And we're going to come up here and I'm supposed to have a pair in here. I won't take no points off this time. But make sure you get it right down that groove, and then we put it at an angle, and then we pull it off. And
you just stripped off the buffer.
I stripped off the buffer coating.
Okay. That's not the
And then, of course, what we would do, you can't see the clad. And then we would take, sometimes it takes several passes. You got to be real careful, make sure it goes right in the glue or you're going to cut it. And then, of course, what we do now is we'll take some green-grade alcohol and we'd wipe that off. But that's the conductor. This is the buffer coating right here. And, of course, that conductor consists of the core and it consists of the cladding, which we cannot see. Those are inseparable. And then this is the buffer right here. So this is what we call a loose buffer. So the buffer, this outside buffer, is not in contact with the conductor. If it's tight buffer, then it would be in contact with the conductor. So this is tight buffer right here.
Okay.
So you can see the coating, the buffer coating where it ends. See
Yeah.
the coating right there? This is the conductor. We need to be real careful. This is glass, guys. And if he sticks in your finger, how long does glass, but a splinter would eventually corrode. This guy here won't.
You stay
Well,
in.
your body actually pushes the splinter out, but it takes forever.
Takes time.
Yeah.
It hurts too.
And then, so this right here would be a tight buffer, right? You understand? This is a tight buffer. So notice here the buffer is actually in contact with the buffer coating. So that plastic, this would be tight buffer. Plastic don't have a buffer coating on it because it don't need that extra support. So this is the actual conductor right here. And of course we can't see the core because the core and the cladding are inseparable. But plastic will not have a buffer coating. Glass will have this buffer coating on it. That makes sense? So what's the function of the buffer coating? To protect the conductor. That's the only thing it's in there for.
It's like a jack.
So what we do here is we use a lot of the term buffer a lot. And tube. They'll call it tight. Some people call this a tight tube. Some people call it loose tube, tight buffer, tight jacket. So all three of those phrases are interchangeable with each other. Okay, you have to step back down. Tight buffer. The inside diameter of the buffer is equal to the outside diameter of the conductor's buffer coating. Except on plastic. Plastic, the jacket is actually, the outside buffer on a tight buffer is in contact with the cladding. On glass, the buffer is in contact with the coating. Add strength to the fiber conductor, easier to terminate and splice, hold broken fibers together. So that coating can actually hold, if we got a break, it could hold it together, right? So this is a single conductor tight buffer cable. So we would have an outside jacket, right? You understand. Then we're going to have some type of strength member. It's going to be some type of Armistead coating. Kevlar is a registered trademark. So this guy says Kevlar, but it might here it is, Aramid coating. So Kevlar is a form of Aramid coating, but Kevlar is a registered trademark. Right? Does that make sense? Are we okay? And then tight buffer jacket. So this is what's nice about the buffer coating is if your fiber breaks, it can literally hold it together. And it might not. The dB loss of the cable might go up, but it still might work enough for you to do this application. Loose buffer, tube or jacket. The inner diameter of the buffer is larger than the outside diameter of the fiber conductor. The lengths of the fiber can be longer than the length of the tube, and it usually is. So your fiber is actually goes up and is actually moving back and forth in there. The tube can contain more than one conductor. Tubes is usually filled with some type of gel to keep moisture out of there. And the coating is usually color coded. And we'll show y'all this. So it uses color codes on the coating. So on this, the coating is just a translucent plastic, right? You understand that. But inside these loose buffered, if it runs multiple conductors, then each conductor, the buffer coating is a different color. And why? So that way we can match it when we get out to the ends, right? So if I hook it up to the red buffer coating here, then that's going to be the red buffer coating on there. Mechanical isolation, resistance to moisture. So this is one big advantage of. So if I'm running my fiber through something that's got a lot of motion in it, like the ground. So if I run my fiber through underground, then odds are it's going to be loose tube. Once I get inside the building and it don't have a lot of motion in here, then it's going to be tight tube, right, or tight jacket. That makes sense? So this guy's a little harder to terminate and splice. For one thing, you need to make sure you get the right, if it's got that gel inside there, you got to make sure you get the right chemical to strip that gel off there. So make sure you look at the manufacturer of the cable and it says to remove the gel, you'll have to have a certain type of wipes. But this guy's very, very sturdy. So this would be loose tube. Are we okay? Loose buffer, loose tube, loose jacket, all those terms mean exactly the same thing. So it depends on where you work. Loose tube dead jump zone, this is not important for us to know. Other cable parts, we're going to have a strength member, right? Outside jacket, inner jacket, gel filling and water blocking compound on loose tubes. Might have some type of binding tape, might have armor output, outside armor. It might be ribbon. AT&T uses a lot of ribbon cables. So what that is, a ribbon cable is, no, ribbon cable just has a standard jacket, and when you look at this stuff, it's going to have a bunch of little humps in it, and then the fiber is going to run down the center. I think I showed y'all ribbon cable in computers, right? It's the same thing, except in what's nice about this is you have a bunch of fibers and they're flat, so you can roll them and make them this way, or you can leave them out flat. And you can get, and these spacing on these little ridges are exact. So what you can do is you can get a ribbon splice, a fusion splicer that might splice 36 conductors at the same time.
Those ribbons are all out. Fiber optic.
What do you mean ribbons?
Ribbon cables.
No, we have ribbon cables in electrical too. They were very popular when computers first came out. Before we went to everything was serial, all your CDs, all your CD players, all your hard drives, these were all parallel. They weren't serial; they were parallel. So you had to get that parallel from your motherboard over to your hard drive, and you wanted it to occupy very little vertical space. So when computers first went to hard drives and stuff like that, and floppy drives, they all use ribbon cables. But a ribbon cable just means it looks like a ribbon, so it's flat. Some people call them flat cables. We got some over there I can show you, but we don't have any ribbon fiber cables. But they're flat cables. And they'll stack them inside there. So when you see them run that big old orange tube, you're just seeing the outside jacket, and that's usually PVC. It's usually pretty hard, right? You understand, these underground cables. And then they run ribbon cables inside there. And why? Because when they splice them, they can splice a lot of conductors at the same time. These are designators. We've already looked at this. OFPN, OFNT. This is non-conductive plenum. We know what the plenum is. What's the plenum?
The area between the roof and
between the fin and ceiling. Originally, it was the return for air conditioning. So some buildings still use the plenum or use that. And that, if you look that up, a lot of people have defined it as that. It's a return between the ceilings for air conditioning. Well, we call that the plenum now, even though we don't use the plenum here. You can see that's why all the slots and everything are cut in the doors right here to return the air conditioning. Then we have jackets that are designed for risers. So OFCT. Now, where's this going to be at? Let's see if we can find this. Should be on the cable. Supposed to be on the cable. So this is riser OFNR. Or OFNR stands for optical fiber non-conductive riser. It's used in riser areas which are buildings, vertical shafts, or runs from one floor to another floor. Cables are not installed in the plenum, so this guy right here should not be run through the wall. Now, why? Well, odds are when this guy right here burns, it emits toxic gases, right? You understand, depending on what they make. And we don't want, and it's not designed for extreme temperature ranges like we would have up in the plenum. So this is UL riser OFRNR. Then it's got a bunch of numbers. Then it's got 0.0051 feet, and it don't tell us much about the cable itself.
OFNP plenum cables can be used as substitutes for OFNR.
But certain ones, right?
since they had.
Yeah, but these are, so plenum cables are rated according to what? Smoke rating, right? Smoke and fire rating. OFCR, I don't know what this is. This is riser cable, flame fire rating characteristics, OFCR cable, but they are conducting armor. So these guys would be inside a metal armor. So we would use these in high stressful, high impact areas, right? OFNG, what's this? This is general purpose cable. Normally they put the conductor side on here too, but I don't see it. This is R. That's G?
That's all.
Oh, yeah. AT&T calls them pigtails. Now I got that name. That's been a use for years. Any short conductor that's attached to something. Mr. Who?
Williams.
There's nobody down here called Williams. Okay. Now let's see. He's probably one of the automotive instructors. Yes. Ford or which? Ford's down there. Chevy's there. Okay. I'm sorry. So this is the way the different types of cables we got, and we got a big list over here on the. This is a really good thing. Came from Fiber. Most of our stuff we buy it from a company called Fiber Instrument Sales, and they provided us with these signs over here that gives you a lot of different types of cables and stuff like that. Loose tube, single fiber. By the way, what we usually do is on these cables, true cables that have multiple conductors, usually they have some type of strength member in here. It's usually going to be like a Teflon or a plastic rod right here. So normally when we pull this stuff, so when I pull, where's that at? So when I pull this, what would we pull it by? What would you think?
Where you what?
If we was going to pull this fiber, what would we pull it by?
What would be cool?
Yeah, what would we pull it by?
Probably the
No. What would we pull it? What would we attach our pulls to? We attach it to this right here. Oops. To the Kevlar. So what we'd do is we would come up here and we'd cut our fiber off. We'd put out a lot of Kevlar and then we'd attach to the Kevlar. And also the outside, maybe the outside jacket. But we're never going to pull with the conductor, right? You understand? If we get into a cable that's got multiple conductors, it is going to have a strength member in it. Either it's a piece of plastic, it's a plastic rod that runs through there, Teflon rod or something that runs through there. And that's what we want to pull by, right? We want to pull by the strength member. We don't want to pull by the what? By the conductor. Because it's glass and it's very flexible, but it's also very thin too. These are just different types of cables, loose tube, and these are some pictures. You can look these up. You can come up here and type in this, you know, loose tube, single fiber, loose tube, multiple fiber. This is what you're looking at here is you're actually looking at the buffer coating right there. And the way they identify the cable, since we've lost the jacket is gone now, right? So what they do is they just make the buffer coating a different color. Because the buffer, loose tube, multiple fiber. So here, this is loose tube. It's only got one fiber. This is loose tube with multiple fibers. This is what they call a central buffer. This would be loose tube, right? This would be ribbon. So notice ribbon, it's just multiple fibers, but they're flat. This is very popular with AT&T because they run in a lot of fiber, but they can splice them a lot at the same time using their fusion splicer.
So,
Yeah, you can see it. You can tell when they're working on their fiber. They got that trailer that they haul around, the little tiny trailer. It's air conditioned. They pull it behind the pickup truck. You'll see these big cables coming in one side. They'll come out the other side. That's what they're doing. They're splicing. You know. So this is a typical ribbon cable right here. So you're not actually looking at the jacket. You're looking at the coating, right? And all the coatings would be what? Would be different colors. What we call a star, a slotted core. And this is the armor coating, right? Y'all see that? Yeah. So this would be sure enough going through some bad stuff. This would be the kind of stuff that they might string on the telephone poles.
They're sort of armor coated.
Huh?
That's armor coated.
Armor coated, but they'll probably injection mold plastic over the armor too, because most of the fiber you see running up there is black. I've seen fiber, some fiber. I don't know if you've ever seen the little machine, but the fiber, they run it down the telephone wires, so now you can see it. So if you look up there at the telephone cable and you see this white thing going down through there, guess what that is? That's fiber. And they got a little machine they hook it up to, and they're down there pulling it on the ground, and it's wrapping the fiber around. So what they're using there is they're using the telephone wire, that big old telephone wire, for the mechanical support. And there's very few now you can't see. Notice it. Don't be driving.
yeah.
Yeah, but the big black telephone wire, now you'll see this white thing, and it's spiraled around there, and that is fiber, guys. And they have a thing that they hook it up to, and it rides on the top, and they have a rope on the bottom, and they pull that thing, and it strings that fiber around the output of that telephone wire. You used to see them all over the place. I mean, you'd see them all the time pulling that thing. This is what we call a breakout cable. Installation performance characteristics: maximum recommended installation load, maximum load that can be applied during installation to the strength members between what?
156 miles.
Yeah. Minimum recommended long-term bend radius. Minimum bend radius for the lifetime of the cable. Rule of thumb is what? So bend radius is given as what? Multiples of the outside diameter. That was one of the questions that y'all missed on that test. I don't know. That was one that was added back in. Minimum, while you're pulling it, minimum short-term bend radius, minimum bend radius during installation is rule of thumb is what? 20 times the diameter of the cable. So when you're pulling it, you don't need to bend it very much. Temperature range for installation or storage, that should be, and the moisture resistance, that should be part of the specs on the cable that you buy, right? Free function of the connection system. This is what we're required to achieve what? Transfer. Yeah, efficient. Fiber retention. And end protection.
Unnecessary damage.
So all our splices and all our termination does this. Precise alignment, make sure the fiber stays inside there and protects the fiber, right? You understand? And we'll look at the different types. This is called a ST connector. Some people call it a Sierra Tango. So this is a ST connector.
Yeah.
And what we call a bayonet connector. So what we have on the female part is we have two stobs that stick out on the side, and then we push this down, and then we turn it and snap it.
And twist.
Twist it. This guy right here is called the ferrule. What's the function of the ferrule? protection, but that's, this guy, alignment, yeah. So this guy is precise diameter. This guy is it's going to align our fiber. Our fiber is this little old tiny dot right here in the center, which y'all can't see on this camera. And this is called the back shell. The purpose of the back shell, of course, is to do what? Connect it. It's not in there for alignment, right? It's in there to, okay. And this right here is called the boot. So that's the three parts. Now this is called an ST connector. This is called an SMC connector. This looks a lot like the connector that you find on your cable TV. So it's a screw type connector. And we're going to talk about pull proof. So this SMC is a pull proof connector. This guy is not. So notice when I come over and pull it, it actually separates from the thing. So that's got a spring in here that literally separates it. So if I come over here and pull on that, what it's going to do is going to pull this ferrule back and cause us problems. So an ST connector is not a pull-proof connector, but it's got a lot. It's susceptible for people actually coming here and accidentally pulling on it a little bit, right? You understand? So we're not going to run these things tight. We're going to leave them loose, right? Because this is not a pull-proof connector. This is a pull-proof connector, so I can come over and hold on my connector and I can pull on it, and this ferrule right here does not move. I come over here and hold this right here and pull on this. Oops, the boot came off. I come over and pull on this one. Can you see the ferrule? Let me get, this is hard. Yeah, the ferrule actually moves. See it moving? So this is not a pull-proof connector. This is one of the most popular connectors out there. The other one that's most popular is what we call an SC connector, which is this guy right here. This is a snap-in connector. So it literally comes in there, and I don't know if you can see the snaps on the side. So this guy right here actually snaps in, but you can see it's not a pull-proof connector either. Okay. But what it does, it gives a little protection on somebody getting grabbed on the cable or something like that, right? So these are the two. One of the two most popular is the ST and the SC connector. This is a bayonet connector. This right here is a snap connector.
So that's the most popular: ST, SC, and LC.
And LC. We got an LC is up here too.
LC is pretty much sort of like an 8-pin connector, where it has a little part that sticks up.
Yeah.
So there's not much difference.
And we've got the different connectors up here. So. But they all terminate. Some of them require, so putting on an SC and an ST connector is exactly the same process. The LC, I've never done one of those, so but I know what it is.
With the equipment we have, it's treated not really much different. You just have a different connector you put on the termination.
So radial, so these are different types of problems we have. Radial misalignment, lateral separation. So our connectors have got to take care of all this, right? So if I've got radial misalignment, it means that the two cores are misaligned, and of course all the light won't get through. If I don't have something that creates the optical path, then what happens is instead of reflecting, when it comes over here and hits this side right here, it's going to come up in here in the cladding, right? And we'll have loss that way. So we got to make sure these connectors touch, or we have something that compensates for that. A lot of your mechanical splices will have what they call an optical gel in there. So the two end connectors don't actually butt into each other. There's actually a little space in there, but inside that space is an optical gel that substitutes for the cladding and the core. Angular misalignment. Most of these are pretty standard. Angular misalignment means if my two ferrules are offset any at all, then that's going to give us angular misalignment, right? You understand? If they don't come in and complete that path, then that's going to be what? Lateral misalignment. If they don't align on then that's going to be radial misalignment. Are we okay? Numerical aptitude index. So the numerical aptitude index determines the angles that these things go. And of course, if we don't have the right numerical mismatch, that means when it goes from one fiber to the next, it's not going to come in at the right angle. Does that make sense? And we might have to reflect, Yeah, so that means all the fiber, if I'm going to connect these two together, whatever the numerical aptitude is for aperture is for this one, then I want to make sure the one that connects to it has the same what? Numerical aperture. Core diameter, this would be if I use two different type of fibers. but you notice, what's the core diameter on this? No, the core diameter. I have no idea. I know the cladding is 125 microns. I know the cladding, but I have no idea what the core is on this, right? You understand? Of course, this is 62.5. I know that. But if I don't know that information, so I come up and get this one. This one does not have a colored jacket on it. So this is AT&T. I don't know. They donated a ton. We got boxes of these things, by the way. So this guy right here is just got a yellow jacket, which to me would mean single mode, but when I look at it, it looks like the core is the same as this one. But this one right here, I have no idea what the core is. I know the cladding is 125 microns. So if I come over here, and this would go inside this same connector, but the problem is if I come over here and match these together in my splice, then I've got I got a core mismatch. And the problem is none of that information is written on here. 7 foot, 2.5 meter pigtail. Now, of course, they ordered the part, and they probably made the pigtail. Lack of cleanliness. So I don't know if you looked at that one. If we look at these guys have been exposed, and when you look at it, you'll see little spots all over it, and that's dirt, right? So we got to keep those things clean. We use syringe grade alcohol, and we use lint-free wipes. So we can't use like toilet paper or something like that to clean these things with.
That explains my problem.
That's why my bandwidth is
lack of smooth surface. So we know we got to, and we can look at these, and that's one of the hardest things to do, guys, is to keep these things from cracking when you sand them. So you got to be real careful.
You gotta sand them?
Mm-hmm.
You haven't done that?
Well, that looks really pretty.
Yes.
So this is the bad one. It'll pass light,
But you can see the spots.
but you can see the spot. So what I want y'all to do is flip this around. This right here is pretty good, but it's got a crack. You can actually see the crack in the core. So they cracked this one while they were sanding it.
You still have to sand them nowadays?
Oh yeah. These are not crimp-on. These are sure enough ST connectors.
You see the dirt over here.
Well, you can't even see the core. So here they didn't polish it.
Oh, wow.
You can see the core, but it would pass light. It's just that it would have a lot of loss in it. So one, it don't look like they polished it enough, or they got it below where they couldn't polish it much.
We can do one more go.
A little bit. Why?
We need to take a break before.
Yeah, I know. We need to.
We went through it.
Yeah, we did. We took some.
We'll cover enough material. We'll have nothing but labs. We don't have a whole lot left to do.
We got on fiber. We're gonna do glass. We're gonna string out some cable and measure the dB loss on the cable just to get a feel of it using the meters. Huh? We got 3 weeks.
Oh,
Well,
you mean next class? I'm like, class is like over now.
Oh, no, we're not going to do anything now. Somebody asked the labs. We have one lab where y'all do as a group, and we'll stretch out some cable over a pretty good distance. We'll measure it off, not with a tape measure. We can just use these floor tiles. They're 12-inch floor tiles. And then we'll use our dB meters just to get a feel on how to use those things. And then we'll terminate. We'll let y'all splice using a mechanical splice. We're going to use what we call an ultra splice. We have 2 types. We have what we call a fiber lock, which is put out by 3M, and then we have a ultra splice, which I can't remember who that is. But, and then we're going to let y'all put on some connectors, some ST connectors. Huh?
Your printing connectors will be compared to what they use at work.
Was that?
I wonder how different the printing connectors you guys use will be compared to what we have at work.
The fiber lock is a crimp connector.
Yeah.
The ultra splice is a twist on. It's really neat. The ultra splice the fiber lock splice is not reusable. That means once you crimp those suckers down, if you need to resplice it, you have to cut it off. The ultra splice it's got a twist on lock, so you can literally use those as long as it maintains a good dB loss. So that's why we use the ultra splice, even though we do have the fiber locks. So these are our splices. We have permanent splices. So a fusion splice. So a fusion splicer literally melts the 2 ends together and maintains the core. It's really, really neat. So we got a camera so you can actually see the splice, which is pretty neat. It does the best splice, but it's a very, very expensive piece of equipment. Then we have a semi-permanent splice, which is what the ultra splice is that we'll be using. So we can come up and we can take it apart. Pigtail we've looked at. So this is pigtail. What your company calls it? What do they call these things? Huh? Patch cable. Well, that's not a patch cable. A patch cable is a cable that goes into a patch panel. So we have patch panels in fiber too. So it's just a panel that's got multiple connections on. So technically this is called a pigtail. And what's nice is that you buy this from a company and it's already been terminated, and it's already been not only terminated, it's also been tested. And then you would use a fusion splicer with this guy here. Fusion splicing is a permanent. Mechanical can either be permanent or semi-permanent. So the one we'll use is semi-permanent, and then we'll hook it. So what we're going to do is so I kind of gave you backwards. We're going to make a cable. We're going to have maybe 3 feet, and we're going to check it and measure the dB loss, and then we're going to splice it last. So you'll take that same cable and you'll cut it in 2, and then you'll splice the cable that y'all made. And this is our fusion splicer. This is our fusion splicer. And this is the ultra splice that we'll be using. So it's real neat. You actually twist these. Depending on whether you put the tie jacket in or you don't, depends on the outside diameter. You need to put that insert in there, not put it in there. We do have the coinage, but we got these somewhere too. We also have the 3M, the fiber lock. The fiber lock is a permanent mechanical splice. So like I said, when you crimp that thing in there, so we have a special little tool that we put it in, we crimp it down, and once it's crimped it down, if it's not a good splice, then what would you have to do? Cut it out. These are called splicing trays for obvious reasons. So the splicing takes away all the mechanical support out there. It takes out the Kevlar and stuff like that. So what we do is we put these things in a splicing tray, And we've got one, a big one that AT&T uses. It's really neat. It mounts underground, and it must have 10 splicing trays in there. And you can see how it does. So you bring your cable with all its support in, you latch it down real good, and then this would actually be the fiber, and then you enclose this in something. And I'll try to remember to bring these over here. This is a big splicing protection. So we got one of these. It looks small, but it stands about this high. Really? Yeah. And it's probably got 10 or 15 splicing trays in there. So they don't splice it and just bury it in the ground. They splice it and put it in something like this. This thing's all sealed up from water protection, and then your trays would be inside of here. And this is what AT&T would put theirs on the ground when they do their splicing. And the different connectors, and we'll look at that next class. Are you okay?
Yeah.
So we have 3 labs that we do in fiber. All right, guys.